Welcome back to another video lesson in Abstract Algebra, and in this lesson we are going to talk about the Lagrange Theorem. In order to prove the Lagrange Theorem, we will be needing the help of cosets, which is another important concept in Abstract Algebra, in particular group theory. Before I begin, let me first apologize for the unnecessary noises because may construction sa itaas. My microphone cannot filter somehow. I don't know how to do it. Alright, so let's start. So here you get a group G, and I want you to fix a subgroup H. On G, I want you to define a relation using the symbol tilde, okay, which is defined for every pair of elements on G as follows. So A and B are related if and only if A inverse times B is an element of H. To illustrate, let me draw it for you. Kunwari, ito si G. Let's say this is G. Then I get a subgroup H. So let's say this is H. How can I know if two elements are related? Let's say this is A and this is B. How will I know if A and B are related under this relationship? Kailangan daw, pag kinampit ko yung A inverse times B, makapasok yung product dito sa H para related sila. Okay? If A inverse B is found somewhere else or somewhere outside H, then they are not related. So, ayun yung relation. Now, para magkaroon kayo ng idea, kapag ang group natin additive, how does this translate? This translates to, kapag additive, minus A plus B, diba? Or simply B minus A. For a while, let's consider the group Z of integers, and let's consider the subgroup 4Z as your H. Alala niyo yung relationship na, so in this case, A is related to B if and only if B minus A is in 4Z. Or we can say that 4 divides B minus A. Naalala niyo yung relationship na ito yung tinatawag na congruence modulo 4. Diba? You can say that A and B are congruent modulo 4 if their difference is divisible by 4. So, yun yung relation na yun kapag nagbigay tayo ng particular na example. Okay? So, we shall show that this relation is an equivalence relation, and an equivalence relation means it's reflexive, symmetric, and transitive. Why is it reflexive? Kasi if A is in G, if you multiply A inverse times A, you get the identity, and because H is a subgroup, E is in H. Therefore, A is related to A. It is also symmetric, kasi if you get two elements A and B in G, and assuming that A and B are related, A is related to B, we can say that A inverse B is in H. Now, because H is a subgroup, inverses of elements of H must be in H. So, yung B inverse A na gusto natin mapunta sa H, actually, inverse pala siya ng A inverse times B. You can try, no? You can actually calculate A inverse B. Inverse is Schoen-Sachs property. P inverse, A inverse, inverse. The inverse of A inverse is just A. Alright? Dahil nga ang inverse ng mga bagay na nasa H ay nasa H ulit, ito ay nasa H. Hence, B is related to A. Lastly, this relation is also transitive. So to verify, you take three elements A, B, and C. Assume that A is related to B and B is related to C. With this, we know that A inverse B and B inverse C are elements of H by definition of the relation. Now, to prove that A is related to C, you need to guarantee that A inverse C is in H. You can do that by trying to observe that A inverse C happened to be, nagkataon, product siya ng A inverse B times B inverse C na parehas ng nasa H. Dahil nga subgroup si H, yung product na yan nasa H. So, A is related to C. We all know that if you have an equivalence relation, This equivalence relation partitions the set, or in this case the group, into nice classes. Ang tawag natin mga equivalence classes. Ang laman ng equivalence class ni A, ito yung mga related lang kay A, no? So, how do we describe the set of all x's which are related to A? Well, it consists of all x so that A inverse x is in H. But if x is related to A, no, if that is true, then this means to say that A inverse x is equal to H for some element of H. And that implies, multiplying A inverse on the left, we get x equals AH. So, as a conclusion, we get the following. The equivalence class containing A happen to be the set of all AH, so that H is in H. So the equivalence class that contains A can be formed by simply multiplying an A to the left of every element of H. With that, in abstract algebra, we write this set as the set AH. Now this is a group element, this is the subgroup. We don't normally multiply an element to a set, but by an element A times a subgroup H, we actually mean every element of H gets multiplied to A on the left. Take note also that the direction of multiplication is important here because a group is not in general commutative. Ang tawag natin sa set na to, we call it the left coset of H containing A. Later, I will show you how to construct these left cosets. Okay, if H is a subgroup of G, then you collect all the left cosets of H, and we know that this because they are equivalence classes of this relation, this in particular partitions G in a nice way. In this lesson, we will be interested in this partition, in what way the left cosets partition G if you select a particular subgroup H. So, if in partition, if two cells are not equal, they are actually disjoint, right? So, two left cosets are equal if and only if the elements containing them are related to one another, and by that we mean A inverse times B is in H. And if they are not related, then these cosets must be disjoint as a consequence of being a partition. In particular, if A happens to be the identity, this reduces, if say this is E, so yung BH mo, H lang, H is equal to AH if and only if A belongs to H, kasi parang identity lang yung isa. Okay, kung may left cosets, meron din namang right cosets. So the set HA, A here was multiplied on the right of every element in H. If you collect those sets, you call it the right coset of H. These right cosets actually are another equivalence classes of a different relation. Kanina, A inverse B is in H. Kung ang gagawin mo, A, B inverse is in H, makikita nyo, it will produce right cosets instead as equivalence classes. Similar properties hold. HA equals HB if and only if AB inverse is in H. And if AB inverse is not in H, then actually kulang ito. This intersection is empty, this joint. And the right coset HA equals H if and only if A belongs to H. In general, AH is not the same as HA because a group in general need not be abelian. But in case where G is abelian, obviously AH will coincide with HA for any A. And we do not have a concept of left and right kung abelian ang group. We just call them cosets. Consider, for example, the subgroup 4Z. What are the left cosets of 4Z in Z? What do we do to get the left cosets? Well, we add a particular element on 4Z on the left. So, for example, if you add 0 on the left, because 0 does nothing, it remains as 4Z. ito pa rin. If you add 1 on the left, lahat ito, mag-add ka ng 1, makikita nyo, ito yung lalabas na sagot. Ang tawag dito yung coset na 1 plus 4z. How do you describe these elements? These are the elements which are 1 more than a multiple of 4. Or these are the integers that leaves a remainder of 1 when you divide by 4. You can also add 2 on the left, and this gives you the integers which leave a remainder of 2 when you divide by 4. Also, you can add a 3 and get this. These are the integers which leave a remainder of 3 when you divide by 4. Of course, I can keep on doing that. I can add 4 on 4z, but if I do that, what will happen? You'll get 4, 8, what else? 0, 12, negative 4, what else? 16, etc. What you're left with is what? It's just again 4z. Because if you add 4 to every multiple of 4, you will still get another multiple of 4, right? So 4 plus 4z is not really new. It's just 4z. It is because 4 is here already. So because 4 is here already, 4 plus 4z will just be the same as 4z. In fact, there are no other cosets. All other elements that you will add to 4z will fall into any of these categories, because in general, an integer can leave a remainder of 0, 1, 2, or 3 when you divide by 4. Nothing more than that. This is why this set of 4 left cosets form a partition on Z, as shown in the diagram. Note, for example, that the coset containing 38 or 38 plus 4z is exactly 2 plus 4z. How did I know that? Because 38 minus 2 is 36 is a multiple of 4. Remember, in this case, a plus h equals b plus h if and only if b minus a is in h. This is the additive version of things that we write in the previous slide. Or it is safe to say that because 38 leaves a remainder of 2 when you divide by 4, then 38 can be found in the coset 2 plus 4z. Hence, 38 plus 4z is equal to 2 plus 4z. In general, the subgroup nz of z has exactly n distinct left cosets. They are nz, 1 plus nz, 2 plus nz, and so on. These are the integers which are multiples of n. These are integers which leave a remainder of 1 when you divide by n. These are integers that leave a remainder of 2 when you divide by n, and so on. And these are those that leave a remainder of n minus 1 when you divide by n. Let's consider a finite group this time, the group Z sub 12 with 12 elements. Consider the subgroup H that is generated by 4. The cyclic subgroup generated by 4 has elements 0, 4, and 8. So the subgroup has 3 elements. So what are the cosets? Take note, because again, this group is abelian, so we don't need to consider right, left. We just say cosets. But for simplicity, we always will look at the left cosets. The left cosets of G, H, and G are the following. 0 plus H is of course H. If I add a 1, no, syempre ang mga gagamitin kong pang-add manggagaling sa G, or sa Z sub 12. This should be Z sub 12. If I add 1 to each one of these, you get 1, 5, and 9. Then I could also add a 2. If I add a 2 to each one of these, you get 2, 6, and 10. Then I could also add a 3. If I add 3 to each one of these, I get 3, 7, and 11. As you can tell, all the 12 elements already appeared in the list, hence, the partition is complete. So these are the 4 left cosets, actually the same as the right cosets of H in G. So it's like getting a subgroup will lead to a particular partition, depending on whether you'll get the left or the right cosets. Let's consider a non-abelian one. So there's a distinction between left and right. Consider the group D sub 4 of the symmetries of a square. This symmetry group is generated by two elements R and S satisfying the following properties. R is of order 4, S is of order 2, and that SR is equal to R cubed S. Let's consider the subgroup H that is generated by S. Because S is a reflection of order 2, it has the following cyclic subgroup. The left cosets of H are, if I multiply, now this group is multiplicative, so we multiply instead of add. Of course, if I multiply ID on H, you get H. If let's say, by the way, let's list down. Before I continue, let's list down the elements of D4. The elements of D4 are, pakisulat sa note nyo kasi mawawala ito, ER, R squared hanggang R cubed, S, RS, R squared S, R cubed S. So, yun yung 8 elements. If I multiply an R on the left, you get R, RS. If I multiply R squared on the left, you get R squared S. Maghahanap ka ng ipang multiply na hindi pa nababanggit sa listahan. So, for example, if I multiply an R cubed, you get the following. Because these are all the 8 elements of D4, so we are done. Meaning to say, there are only 4 left cosets. Laging 4, no? Hindi ko sinasadya. Nagkataon lang. On the other hand, eto na. Kasi nga, non-abelian yung group, huwag mo nga asahan na parehas yung lalabas. Except, of course, identity. Kasi, ang identity, pag minultiply, yun pa rin. Pag kinumpit ko yung HR, R is multiplied on the right. You get this, right? R, SR. But what is SR equal to? R cubed S. So, as you can see, si HR tsaka si RH ay magkaiba. Diba? Ito HR, ito red horse. Hindi, joke lang. RH. Diba? O, tignan natin si HR squared. Saan equal yung SR squared? Ang SR squared, naalala nyo dito sa group na ito, may isa pa tayong equality. Yung SR to the K is R to the 4 minus K S. Ito yung ating formula. Kaya kapag meron kang SR squared, you get R 4 minus 2S or R squared S. Oh! Meaning to say, nagko-commute si S at R squared. Oh, hindi pa masama mangyari yun. And finally, HR cube, yan ito, saan equal yung SR cube? R to the 4 minus 3S, so RS. Ayan. So, ipapakita ko nga ngayon sa inyong dalawang partitions na ito. And they are kind of different. So, kita nyo, no? The way the left cosets partition the group, in this case, is not the same as the way the right cosets partition the group. So, this is what I'm telling you. The left cosets and right cosets coincide only, well, does not coincide in general, especially when the group is non-abelian. In fact, there are instances where the left and the right cosets are basically the same even when the group is non-abelian. And that is a topic for another lesson. Kailan nangyayari yun? Or kailan parehas ang ginagawa ng left cosets sa mga right cosets? Okay, but let's forget about that first. Let's observe that the cosets of a subgroup have the same cardinality of the subgroup. Meaning kasi, pag yung subgroup tatlo ang laman, napansin nyo sa mga examples ko, tatlo lang ang laman ng mga ibang cosets. Pag, dalawa lang ang laman ng subgroup, lahat ng cosets mo, dalawa lang ang laman, mapa left or mapa right. The reason is because if we pair up the elements of H and the left coset AH using the following pairing, na si H, i-map mo sa AH, kung right cosets naman, si H i-map mo sa HA, you can check that these functions are bijections. Ano ba? Ba't siya 1 to 1? Kasi kapag meron akong f of h1 equals sa f of h2, that means to say ah1 equals ah2. But we are in a group. There's a left cancellation law. LCL now guarantees that h1 is h2. Obviously, h is surjective or onto, so we're not going to check. Yung pagiging injective naman or 1 to 1 ng G dahil naman yun sa right cancellation law. Hence, ano ngayon ang consequence? In other words, the coset will partition the group. Let's say finite yung group, 12. Meron kang subgroup. Hahatiin niya ngayon into m parts. Magkakasing dami yung part. What does that say about the subgroup? Yes, the subgroup must have an order which divides the order of the group. Meaning to say, if G is a finite group and H is a subgroup of G, then the number of elements in H must always divide the order of G, or the number of elements in G. Naintindihan nyo? Tingnan nyo yung mga examples natin ng subgroup. Kung halimbawa order 12, may subgroup na order 4 for example, and 4 divides 12. Okay? Ba't kaya siya ganun? Or ba't siya totoo? Ito yung proof. Since G is finite, yung subgroup na H will only produce finitely many left cosets. Kasi nga, pinapartition ni H, ng mga cosets ni H, si G. So, ilang cosets meron? Finite lang kasi si G mismo, yung binubuo ay finite lang. Kunwari ito yung kumpletong listahan ng mga left cosets. Of course, one of these is equal to H. By the remark observation, kasing dami lahat ito ng H. Hence, because G is partitioned by these cosets, union siya ng mga cosets na to. So, yung number of elements in that union is the same as the number of elements. Partition nga. These are pairwise disjoint. So, the number of elements in the union is just the sum of the number of elements in each of the classes. Lahat sila kasing dami ng H. H yan. Ilan yan? M. Hence, this is the same as M times the order of H. So, therefore, the order of H must divide the order of G. Ganun lang kadali. Kasi nga, meron na tayong tool, yung mga cosets. Now, one of the fast consequences is the fact that if M does not, kapag yun naman contrapositive, no? If M does not divide the order of G, then G cannot have a subgroup of order M. Let's say meron kang group of order 12. Alam mo si 7, hindi naman dinidivide si 12, right? So, you cannot have a group of order 12 cannot have a subgroup of order 7. Ang mga possible orders lang, 12, 6, 4, 3, 2, and 1. Pero, sinasabi ko ba na automatic meron kang subgroup of order 6, 4, 3, 2, and 1? Well, mamaya, pag-uusapan natin yan. Ito muna yung mga immediate consequences. For a finite group G, every element of G has an order, which is also a divisor of N. Ano yung N? Okay. Lagyan natin dito, of order N. So, si N ay order nung G, ha? So, lahat daw nung mga elements, di ba? May kanya-kanyang order yun. Yung smallest positive integer so that A raised to N is equal to E. In fact, kapag lahat ng element ng group mo, ni-raise mo sa N, where N is the order of the group, no? It will be equal to the identity. Ang reason is because if you have an element, you consider the cyclic subgroup that it generates, it is a subgroup. Therefore, by the Lagrange Theorem, its order must divide the order of G. This is wrong. And since the order of the element is equal to the number of elements in the cyclic subgroup that it generates, then basically the order of A divides the order of G. Finished. Eh, bakit totoo yung second claim? Ito nga. Kasi nga, the order of G is N. Let's say, because the order of A divides N, you can write N as K times the order of A for some K. Hindi yan absolute value, ha? It's the order of A. So, by definition of order, A raised to N is A raised to absolute A. Order of A times K. But, you know, A raised to the order of K, by the law of exponents, is identity. Ang A, pag na-raise mo siya sa kanya order, maging E, di ba? E raised to K is just E. So, pag meron kang group of order 39, lahat ng elements na-raise mo sa 39. Lahat yun magiging identity. A specific consequence is the fact that if the group G is of prime order, why is this nice? Kasi kapag daw ang group ay of order P, where P is prime, automatic yung group mo cyclic. Isn't it nice? Alam mo kaagad, kapag cyclic, very simple ang structure niyan. In fact, lahat ng cyclic group of order P isomorphic lang sa Z sub P. That's what I'm saying. Why is that? Kasi kapag si G ay may order P, tas yung P ay prime, syempre, ang P greater than 1. May at least 2 elements ka. Kumuha ka ngayon ng kahit na ano na hindi identity kasi nga meron kang at least 2 elements. Let's say A. By number 1, the order of A must divide P. Since the order of A cannot be 1 kasi hindi siya identity, and P is prime, ano ba mga nagdi-divide sa P? P and 1. So the order of A must be P. Therefore, A, if it has order P, it generates a cyclic subgroup of the form EA squared up to A to the P minus 1. Alam niyo yan. This is our theorem before. But this subgroup already has P elements and therefore must be equal to G. Therefore, G is cyclic. It is generated by some element. In fact, for a group of order P, lahat ng mga non-identity element, lahat sila generator. Yun yung nakita natin dito sa number 2. Okay? Another consequence is the fact that if G is a group with 4 elements, nakita niyo mga groups natin na 4 elements, dalawa lang ang structure palagi. Kundi yung cyclic na Z4, nagiging Klein 4. Ano nga yung Klein 4? Yung Klein 4, E, A, B, C. Ang katangian ng Klein 4 ganito lahat sila order 2. Order 2, so E yung diagonal. A, B, C, A, B, C. So, dapat ito C, B, A, ito C. Ito B, A. Diba? Yan ang katangian. Ang Klein 4 nakikilala sa fact na group siya of order 4, tapos lahat ng elements order 2. Pag alam mo yung fact na yun, mabubuo mo na yung buong table. No? Yeah? So, Klein 4 siya. Using the Sudoku property. So, bakit ganon? Kung si G ay cyclic, tapos na. Z4 ka. Paano kung hindi? Kung hindi siya cyclic, we will show that G is Klein 4. Isomorphic to the Klein 4 group. First of all, if G is not cyclic, it cannot have an element of order 4. Otherwise, it will be the generator. Wala nga generator, not cyclic. So, the Lagrange Theorem implies that each non-identity sa group, ang order 1 lang identity, diba? So, yung mga non-identity, anong order? Dapat divisor or divisor ng 4. Ano mga divisors ng 4? 4, 2, and 1 lang. Cannot be 4. Cannot be 1. Therefore, 2. Lahat ng non-identity element will have order 2. Yeah, almost Klein 4 ka na. Nakita mo na bakit Klein 4. Kuha ka ng dalawang non-identity element na dalawa yan. So, hindi sila parehas. Bakit may dalawa? Kasi nga, may tatlo kang non-identity element. Lahat yung order 2. Makakuha ka ng dalawa. As you can see, hindi pwedeng maging identity ang AB. Pag minultiply ko sila, cannot be identity. Otherwise, magiging inverse ni A ang sarili niya. Diba? At si A mag-equal kay B. Hindi nga eh. Si A ay hindi B. So, AB cannot be the identity. Hindi rin naman pwedeng maging A yung AB. Kasi kapag ang AB ay A, magka-cancel yung A, B will be the identity. Again, a contradiction. Same fashion, AB cannot be B because if they are equal, B will cancel, A will be the identity. So, bawal yun. Kasi non-identity nga sila. Therefore, ang apat na elements ng G ay ito. So, how do we multiply this? Para makita natin na line 4, sulat mo, E, A, B, A, B, E, A, B, A, B. Identity yan. So, ganyan dapat. B, A, B. E, E, E. Lahat sila order 2, di ba? Ano yung A, B? It cannot be, well, A, B yun. Ano yung A times A, B? A squared B. Diba? A squared B. Ang A squared ay E, kaya ito ay B. Yeah, B. Naguguluhan ako. Lagyan ko ng guhit. Ano naman yung B, A, B? Ano yung B, A, B? Tingnan natin. Ito ba si A, B order 2 din? Kasi non-identity. So, ang A, B ay inverse ng sarili niya. But by shoes and socks property, B inverse, A inverse yan. Order 2 ulit si B at si A, so self-inverse, BA. Hence, abelian si G. Finally, because ito ay ganon, at ang BAB, abelian nga, magiging B squared A, ang B squared ay EA. So, we can conclude, mako-complete mo yung table, makikita mo, magmamatch siya doon sa line 4. And we are done. Anong conclusion? Okay. Order 1, isa lang naman talaga ang group. Yan. Order 2, 2 is prime. So, Z sub 2 lang. 3 is prime. Z sub 3. Order 4, na-prove natin ngayon, dalawa, Z4 and line 4. Order 5, line, cyclic, kasi prime ulit. Diba? C5. Ano napansin nyo? Although, isa lang yung hindi cyclic dito, which is line 4, lahat yan, abelian. Kaya lahat ng group na may hindi hihigit sa 5 elements ay abelian. As a consequence, mayroon tayong nakitang non-abelian group of order 6, yung S sub 3, o kaya yung D sub 3, isomorphic kasi sila. So, we can now say that the smallest non-abelian group is S sub 3. Now, okay, you can pause kung napapagod na kayo, ha? And continue afterwards. Now here, we're talking about another, a subgroup of G. One checks that if we pair the left coset AH to the right coset HA inverse, you can prove that this mapping is a bijection between the set of left cosets and the set of right cosets. Meaning to say this mapping will be onto and 1-to-1. Okay. Now, being said, sabihin, magkasing dami daw yung left at right cosets. Kung may 4 kang left cosets, 4 lang din ang right cosets ng isang subgroup. Yung number na yun is what we call as the index of that subgroup. Kung ilang cosets ang magagawa niya, left or right man, kasi parehas lang daw yun. You call that the index of the subgroup H, and it is denoted by this symbol. Anong binibilang nito? Kung ilang cosets ang magagawa ni H sa loob ng G. So it seems like may formula tayo kapag si G ay finite. So let's say 12 yun naman ni G. Si subgroup mo 3 elements. Remember, ang mga cosets niyan tigta-3. Ilang cosets ang kakasya? 4. Paano natin nakuha yung 4? 12 divided by 3. Mamaya makikita niyo yan. Pero hindi naman laging ang group ay finite. Kagaya nito, yung group mo ay Z. Pero nakita mo yung subgroup na to, merong 4 na cosets kahit na infinite yung Z. So, hindi laging finite palagi si group. Ha? But we know that it has 4 cosets, so the index is 4. In general, the subgroup NZ has index n. Meron kasi siyang n na cosets. Ito yung sinasabi ko. Kung finite lang naman si group, bilangan mo lang kung ilan yung nasa G, bilangan mo lang kung ilan yung nasa H, i-divide mo kung ilan yung quotient, yun yung index. Halimbawa, ito. Anong index ng subgroup generated by 27 sa loob ng C sub 36? Oh my gosh, ang hirap naman yan, sir. Hindi, meron tayong mga formulas, diba? Cyclic group yan eh. How many elements are there in Z36? 36. How many elements are there in the subgroup generated by 27? May formula kayo. 36 divided by the GCD of 36 and 27. Pansin nyo na mag-simplify yan sa GCD lang ng 36 at 27, which is 9. So, itong subgroup, ito may siyam na coset sa loob ng Z36. Paano naman kapag ganito? Meron kang G, subgroup niya yung H, tapos si H may isa pang subgroup na K. Siyempre, may index ito, no? For example, yung index ni H sa G, ganyan. Ito yung si K naman, as a subgroup of H, may index din na H colon K. Si K, subgroup din naman yung G, so may index to na G colon K. So, we're asking here, may relasyon kaya itong tatlo? Of course, there is. Kung si G ay finite, ito kasi siya, kung finite. You can rewrite this, no? Parang ganito yan. Para kasi magka-cancel yung H. Ito ngayon yung index ni H sa G. Ito yung index ni K sa H. So, ito yung relationship. Okay? Pero alam niyo, itong result na totoo kahit si G ay hindi finite. Yun nga lang yung proof ay, well, hindi madali yung case when G is infinite because it involves cardinal numbers. So we will skip that case and we call that theorem as the index theorem. Okay? Meron tayong ganung relationship. Siguro, you might, let's illustrate the index theorem in a particular example where G is not finite. Halimbawa ito. 8Z is inside 2Z. 2Z is inside Z. We know that 8Z has index 8. 2Z has index 2. Both in Z. By the index theorem, kung kukalkulate mo yung index nung 2Z nung 8Z as a subgroup of 2Z, that should be, ito yung nanggaling sa index theorem, 8 divided by 2, and that should be 4. Sabihin si 8Z raw, although may 8 siyang coset sa Z, kasi yung 2Z kalahati ng Z, parang ganun yan. Diba? Kalahati even, kalahati odd. Right? Kasi nga, yung kalahati lang ang bubuuin mo, imbis na 8 cosets, 4 lang ang kakailanganin mo. Ano yung 4 na yun? Well, ito yung 8Z. 2 plus 8Z, even pa rin ng mga yan. No? Hindi ka pwedeng mag 1 plus 2, 8Z. Kasi ang 1 plus 8Z, meron tong mga odd integers, and that's not part of 2Z. Kung mga hindi ito subset ng 2Z, so not included. You could also have 4 plus 8Z, and 6 plus 8Z for that matter. Ito na yung bumubuo sa lahat ng mga even. Ang union yan, yun yung 2Z. Do you understand? Ito na. Sinasabi ko. Although the Lagrange Theorem is very much powerful sa pag-analyze ng mga finite subgroups, no? Isang finite na group. The converse is not true. Meaning to say, halimbawa, I have a group of order 12. I know that I have a group of order 12. I know also that 6 divides 12. The question is, can I be guaranteed that there will exist a subgroup of order 6? Ang Lagrange theorem kasi ganito. If you get a subgroup of a group of order 12, then that subgroup must have an order which is a divisor of 12. We are asking the converse. what I mean to say is, let's say may group of order 12. I know that 6 divides 12. Can I be guaranteed of a subgroup of order 6? Unfortunately, no. In fact, meron tayong counter example. And this is the smallest counter example I know. I think this is the smallest counter example. The alternating group A4. Ano laman ng A4? Bale, ang A4, again, kung di nyo natatandaan, balikan nyo, kalahati ito ng S4. S4 yung mga permutations on 1 to 4. Ang laman lang ng A4, yung mga even permutations in S4. Meron siyang 4 factorial divided by 2 elements or 12. Ano yung 12 na yun? Ililista ko. Nilista natin to dati, pero ito ulit. Yung identity. Ang source natin ng mga even permutations, mga 3 cycles. Actually, add cycles. No? Meron kang 8 3 cycles. Lahat sila order 3. At yung mga product of disjoint 2 cycles. Yung 1, 2, 3, 4, even to, even. Ito, take note, ito yung order 1. Ito lahat order 3. Ito, anong order nito? Pag meron kang A, B, C, D, anong order nito? As you can see, pag inulit ko yan, pag in-square ko, let me erase for a while. Paging A, B, C, D, A, B, C, D, dahil nga disjoint yung mga cycles na yan, paging A, B, C, D. But remember, these permutations undo one another. So, identity. So, in other words, itong mga to order 2. So, meron kang isang order 1, 8 order 3, 8 order 3 elements, and 3 order 2s. Okay? Alright. Now, here, we claim that A4 cannot have a subgroup of order 6. And to prove that, we will do it by contradiction. Kunwari, si A4 has a subgroup H of order 6. Mangyayari. So, ipabakit, kukuha ko ng arbitrary na 3 cycle. Kukuha ka ng kahit alin dito, let's call it sigma. Dahil si sigma ay order 3, pag kinam yung mga powers ng sigma, tatlo lang ang lalabas na powers, identity, sigma, sigma squared. Ang sigma cube identity na yon, sigma to the 4th, sigma lang yon. Ulit-ulit lang. So, meron lang tatlong distinct powers si sigma. Dahil nga may tatlong powers ng sigma, mga cosets na mabubuo mo kapag yung mga powers ng sigma minultiply mo sa h, tatlo lang. H, sigma squared h. Pero si h ay order 6. So, anong index niya? 12 over 6 or 2. So, meron lamang dalawang coset si h sa loob ng A4. Order 6 na siya. Tatlong cosets to. Mali ba yun? Hindi. Ang sinasabi lang nito, yung dalawa dito sa tatlo, equal dapat. Kasi h can only have 2 cosets, left cosets. So, yung dalawa dito sa tatlo ay equal. So, pwedeng ito, pwedeng ito, pwedeng ito. So, let's look at cases. Kung equal itong dalawa, no? Property ng equality, si sigma dapat nasa h. Kung equal naman itong dalawa, multiply ka ng isang sigma, sigma h equals sigma cube h. Ang sigma cube identity yan. So, sigma h is in h. Again, that will imply that sigma is in h. So, kung ito equal, ito in-imply. Kung ito equal, ito in-imply. Kung ito naman ang equal, left cancellation law, it will imply that sigma h is h. Again, sigma is in h. In other words, in any of the cases, the conclusion is that sigma is in h. Para mong sinasabi ngayon na lahat ng 3 cycle mo, kasi kumuha ka ng arbitrary na 3 cycle, ay nasa h. Pero pwede ba yun? Meron kang 8 3 cycles, but you only have 6 elements in h. That's weird. Kasi nga, si h ay 6 lang ang laman, ang ma-accommodate, pero lahat ng 3 cycles mo nasa loob, no? By assuming that A6 has a subgroup of order 6. Therefore, that cannot be. Kumbaga, ang sinasabi ko, if A4 would will have a subgroup of order 6. Lahat ng mga 3 cycles mapupunta doon. Right? As a consequence of Lagrange. So, dahil meron kang 8, evidently meron kang 8, yung, yung wala mo nagkasya sa 6 contradiction. So, therefore, A sub 4 cannot have a subgroup of order 6. Alright? So, that's it for this lesson. Problem set is coming up. Be prepared. So, if you have questions, you can always send me an email or you can always chat in our Google Classroom. Maraming salamat. See you in the next lesson.